Okay. Hello, everybody. Good morning. Thank you for assisting to this workshop, which will be focused on manufacturing to gain Industry 4.0 benefits as part of the dissemination activities in the framework of the Level Up project. Just a quick reminder, the aim of the Level Up project is to offer a scalable platform covering the overall life cycle, ranging from the digital twins setup, modernization actions to diagnose and predict the operation of physical assets, the refurbishment and remanufacturing activities towards the end of life, in-situ repair technologies, and the redesign for new upgraded components will be facilitated through virtual simulations for increased performance and lifetime. Today's workshop is supported by the DFA, Digital Factory Alliance, an initiative to support the digital transformation in the manufacturing sector. I would like to take 1 minute to introduce what the DFA is and how it can be beneficial for you all. I'm going to share my screen now with this one. The main objective of the DFA is to support the digital transformation of the companies in the manufacturing industry. It's used for dissemination and exploitation of results. It is an initiative that focuses on technological providers, end users, digital innovation hub, and the testing and experimental factories. If you are, for example, a technical provider and you have solutions and innovations that are mature enough, we offer catalogs where you can get to end users who can buy the solution. If you are an end user, a factory that is looking for products in order to support its digital transformation plan, here you can find these products for these technical solutions. They're also installed in the factory. We have a digital innovation hub, which is an additional service where both catalogs and services are offered to make companies more innovative and for detecting and experimental factories. These are just the laboratories and entities that are going to certify the products placed in the DFA. There are 4 main services that we have in the DFA, which are the Body of Knowledge, Innovation Campus, Flagship Initiatives, and Business Network. We have different catalogs for exploitation, like the Innovation Catalog, where the results from R&D projects are placed and components developed in those use cases with descriptions and
sorry to interrupt, but we cannot see your screen.
Oh, you can't?
Sharing something.
Oh, okay, let me see. Do you see it now?
Yes.
Okay, let me go back so that I can do it again, make it more properly. This is the DFA. These are the 4 main services that I was talking about: technological provider, end user, the digital innovation hub, and testing and experimental factories. Then I went up here, and here are the services: the Body of Knowledge, Innovation Campus, Flagship Initiatives, and Business Networks. And then this is the section that I was discussing, which is the Innovation Catalog. Once you go inside, you can also see the use cases and you can see the components. And then if you click on one of them, when you go inside, you can see all additional information like the developer, the type of platform, like if it's a software, hardware, you can see a short description, you can see what it was used on, and you can also see some pictures. If you go back, we also offer events like the one that we're hosting today, but we have another one coming up next week. You can see the past events, and you can also subscribe to a newsletter to be up to date with the latest news. Going back to the presentation now, I'm going to make sure that you can all see the presentation too. Can you see my presentation?
Yes.
Perfect. So pretty much in today's workshop, we'll cover up how Level Up delivers an operational and refurbishment framework with a particular focus on the retrofitting of legacy industrial equipment to enable them to benefit from Industry 4.0. This is done through the implementation of modernization actions for interoperability and deployment of a scalable digital platform that offers a wide range of capabilities, including components for improving maintenance, practices and optimizing dynamic utilization for sustainability. The integrated IoT stack, which includes diagnostic and prognostic modules for PDM application, it plays a crucial role in this process. In particular, sensor gateway layer by SEMSAP, middleware, Holonics, semantic mediator, Viva, machine forecasting in the core, predictive maintenance platform by Lenis, and detect and predict by Viva, which are level-up components that work closely together. For these, what are their features and what outcomes have been generated for the project? We're going to have 2 pilot demonstrations. We'll go into more detail and we'll showcase the results. As you can see in our agenda, we're going to start with SenseApp, then we're going to follow by Holonics, Viva, Atlantis, Core IC. We're going to have a Q&A session. Then we're going to discuss the 2 pilots, and then we're going to end the workshop with another short Q&A session. Let's start with Giorgio Kouzes from SEMSAP with the topic of sensorization. Giorgio is a senior researcher at SEMSAP Microsystem. He's an electrical and computer engineer, has experience in the field. Giorgio is also listed as a researcher in SEMSAP SA. He has expertise in areas such as artificial intelligence, machine learning, and Industry 4.0. Additionally, Giorgio Kouzes has been involved in projects related to predictive maintenance. He has published research papers, and he has been cited in various academic cycles. Giorgio, the floor is yours. You can now share your screen.
Hello, everybody. Wait a minute to share my screen. Okay, can you see my screen?
Yes.
Okay. Today I will talk for the data collection layer, the sensorization, as we call in the webinar. In practice, we have 3 different, not 3 different, the sensorization part contains, let's say, 3 layers in the data collection part: sensorization, synchronization, and gateway. I will explain later for this. Some words about SenseApp. Our headquarters are in Swiss. We focus mainly for the automatic shop-floor data collection, production monitoring, quality, and performance inspection. Our target industry is mainly the folding carton industry, printing and packaging industry, and pharmaceuticals and cosmetics. We have a variety of participation in EU industry. And we come in this project with an edge solution. This solution is modular, mainly is developed through and furthermore developed in this project. The modular solution mainly contains a set of sensors and a set of data collection solutions for the field. Data pre-processing, real-time monitoring, and gateway, let's say, functionality. As I told you previously, in the level up, our role is mainly the contribution of the modernization of the production line. Let's talk now about the modernization and sensorization. First of all, this is part of the protocol Z that is defined in the level up. Protocol Z, the main, let's say, input for the protocol Z are the definition, the requirements, the user requirements. So it can be pilot driven, and based on these requirements, and having in our mind that every pilot has a specific situation, the as-is situation, and specific architecture, we plan to modernize this pilot without affecting the existing situation. So we try, based on the protocol Z, to put the modernization in the existing architecture and extend this architecture. Except the definition of the new, let's say, architecture, we have another part, the middleware part, and finally the modernization part. The middleware part will be discussed and presented by Stefano to the next session. Now we will talk about the modernization part of the Protocol 0. The scope of modernization is to observe, to process and transform, to visualize, and finally to transfer the data that collected from the field to the middleware. So finally we can achieve that this pilot line can be level up ready. What does this mean? This means that the whole architecture and functionality of level up can be deployed and used in the specific pilot. Regarding the observation, the plan is to use existing sensor, acquire data from existing sensor, install new sensors where are necessary based on the requirements, and also gather data from machineries. Of course, if this can be provided by the machineries that already exist in the production line. The process and transformation part mainly focused to homogenize this data. And of course, this is a part where a variety of edge protocols are used. And finally, we tend to hide, let's say, to add an abstraction layer to this part in order to hide protocols to the lower level. The visualization is mainly focused to produce dashboard and give this real-time information to the operators in order to help them for condition monitoring. The transfer is finally, as I told previously, after transforming the data from physical, let's say, electrical signals to a specific structure that can be sent to the middleware, we are using here JSON format. All this we can see that has a high complexity because every pilot has different requirements, different initial architecture, different variety of machineries, different processes. So the modernization part is not a simple, let's say, task. For this, in order to face this complexity, we split it, the whole modernization activities in three abstraction layers. The lower layer is the sensorial layer, where, as I mentioned previously, we have new sensors, existing sensors or machineries that can provide data. The second layer is the CPS layer, cyber physical layer, where we have the control units or process units inside the industry. Here we can have machineries or a software that is executed in this layer. And finally, the upper layer is the gateway layer. The gateway layer links the edge part with the middleware part. Here we can see that except the equipment of gateway equipment, we can have a list of software or hardware that support this gateway. Yes, this is the final one. So the sensorizations, modernization of the with the protocol 0 activities and these abstraction layers, we can achieve the sensorization of every pilot line in a more formal way. To the next, we can see an example of sensorization, mainly in the next session of the webinar that is related with the pilot ISO call. I don't have, if you have any questions, otherwise I can give the floor to the next, which is Stefano, if I'm not wrong.
We can continue since we have a short Q&A session. So let me share the agenda real fast, and we can start with the next speaker.
I think that Marco Frank can start the session, and then I will take the floor.
So now let's move to middleware with Stefano Borgia from Holonix and Marco Franchi from Viva. Just to give you a little insight of these two people, Stefano is a project manager engineer at Holonix, spin-off of Politecnico di Milano. He's an author of articles on digitalization and collaborative robotics, published in well-known journals such as Integrated Automation magazines. Additionally, he has written articles on data integrity in Industry 4.0 for Data 4.0. Marco works as a research scientist at Viva since he joined Viva in 2009. He has been involved in several German and European projects. They are related to the development of semantic interoperability approaches. In addition, he is one of the leading researcher scientists which developed and maintained SIMD as part of the firmware ecosystem. Stefano, Marco, the floor is yours.
Thanks a lot. I will share my screen, I think. Okay, give me one second. Can you see the right screen?
Yes, now yes.
Yes.
Okay. Go. Then I will start with the presentation together with Stefano Borgia. Sorry. The background is in principle Industry 4.0 is one of the key enablers which helps us to achieve the flexibility and adaptability in the future production processes. This is what is needed for the current way of productions in Europe. The key challenge is here that we need an informatization and digitalization of the production environment. That means, in principle, what we need is that each of the tools, software, machines, and so on be smart and can be interact with the complete environment to enable this kind of flexibility and adaptability. Because the reason beyond this is naturally we need status information of a machine, of a planning tool, and so on to make decisions on time to reduce failures and so on. That means in principle what we need to do is, as already introduced, we need to get in the state where all of the machines, the old one and the new ones, get smart. Smart means that they can send their status information to everybody, that they can interact with everybody, receive or resolve controls, and so on. And that means what we need to do is we need to be smart. We need to support separation. And this, if it goes this way, then we have to take some data integration challenge into consideration, because if everybody can talk, then unfortunately we have in a production environment and different data formats and schemas for the existing legacy systems, like an ERP, PPS, the condition monitoring tool, and so on. And we have also different machine vendor specific data formats and data schemas for the new machines or the old ones, which are now smart. That means we have a couple of different formats, different schemas, different technologies, in one environment, and everybody needs to talk to each other. That means what we have at the end is a huge integration effort to get everything or to put everything together, and this kind of way forward has a huge impact for the whole IT infrastructure, for the setup and also for the maintenance if something changed, which is desired if you go to the way of flexibility and adaptability. For this, we propose the solution with the middleware. And for this, I hand over for Stefano for the next slide.
Yes, thanks, Marco, for the introduction. Here we are going to speak about the approach of data integration that it is in a view of combining data residing in different sources from one side. So you can consider the data that are coming from the fields, from the machineries that are sensorized with the modernization approach that has been introduced by Georgios before, or the sensor, the devices on the field, and from the other side, we can consider the IT components or systems that are present into the company, for instance, legacy system, ERP, and so on. And from the other side, the vision of data integration must provide user to a unified view of the data that is going to collect. Basically, we are proposing here a middleware as a layer for enabling the communication between the different modules for the big data management, so for managing the persistency of the data in a certain way, with a certain format. The middleware is able to monitor the devices that are producing the data, so the machinery, the industrial assets that are on the field. And the other aim is to basically handling the data that are coming from different sources in a real-time way. Just a further words in consideration to the previous slides. Basically, in order to collect the data, we need to define models. So some entities in order to manage both the data that we are collecting, but also the devices and the real machinery that are the producer of the data. So basically, we are leveraging an IoT model that consider devices, device type, and so on, and the specific semantics in defining the data structure that can model the data and validate them. Considering these slides, here we have a list of the services that are exposed by the middleware. This part of the middleware is the one related to the sensor data, and so to, let me say, the not complex data. The middleware is leveraging a microservice architecture, basically as a foundation, and is providing a data collection layer towards the fields. It can have a direct communication with the devices or an indirect communication delegated to the gateway. For instance, consider the approach introduced by Sensat before, and the use of the gateway layer as an intermediate node to make also some edge-based processing facilities that are in any case contained also into the middleware. We are exposing a data streaming platform to support reactive data processing, but also the application integration. So the modules that are delegated to the analysis of the data can interact with the middleware considering this platform, but also by retrieving historical data from the long-term time-based data storage repository. And so we have also capabilities in terms of data persistencies and also in terms of filtering and retrieval of the data. Of course, it is needed to also assure the internal security, and so it is present a part of cybersecurity that is leveraging dual protocol and the key component addressing authorization and authentication issues. And in considering the middleware level, we can enable the full interoperability of the data that are flowing towards the middleware, and also the possibility to annotate the data, so to improve the content of the data by leveraging the metadata in order to enrich and extract value from the data that are flowing. So I think this is the part of the middleware for sensor data. I can give the floor to Marco for the part of semantic mediator and complex data management. Thanks, Marco.
Okay, thanks. Okay, also in principle, what we heard is that from the data integration side, that means we can use the middleware and to combine different data sources into one source. This is great, because that means on the side of the different protocols, we can just solve the data heterogeneity and the protocol heterogeneity. If we have everything, let's say in one channel, we have still the issue that we have different data formats and data schemas and different way of terminology. That means if we can also solve this issue, then we really achieve this kind of interoperability on the data layer, and we can share this data now as information for the ongoing services, mainly the data, different services which needs information, needs robust interfaces for their way of working. For example, production planning, decision making, predictive maintenance, and so on. It means what we need is interoperability, and it is defined, it's a very old definition. It's defined as the ability of two or more systems or components to exchange and use information. And this term information is really what we achieve is a semantic mediator in this place, that independent from the incoming data, the semantic mediator translates everything into information, which can be then seamlessly integrated into the following services. This is what we do. You see in the figure an example that in principle, independent what it's stored or it's sent, it's either it's a CSV, JSON, XML, or something else. At the end, the output is the same. It means at the end you have just one specific interface API, which can be then used for the integration. What we do is in principle to come from the data to the information view, we introduce for the specific data sources, also specific machines and so on, wrappers. A wrapper enables in principle the translation of one specific data source, something like all JSON files or XML files, into one information, which is then described as ontology. Ontology is the way forward of a semantic web, how to can describe information and then keep a very unique and not ambitious meaning of the information of the data. These wrappers we introduce for one type of data source. That we want to do is that we add to this kind of wrapper for each specific data source something like a self description. That means the wrapper describes the data source and say in this data we have this information. It is stored in this data field. And I also describe how you can translate the data into this information as part of an ontology. So it means this wrapper includes a self-description. The self-description is just a configuration which can be extended over the time. That means if something change on the data side, you just need to replace, let's say, this configuration, but not to update the tools. And you are then already up to date for the complete information flow. This is what we offer, and this approach in principle guarantees the separation of the data sources and the dependent tool chain. That means we really achieve a robust information flow, which is stable and can be used in a very flexible world, in an open dynamic world, where everything changes very quick. To give you the complete picture, we're starting on the pilots. For us, this can be one pilot or a couple of pilots. Each of them has different machines from different vendors. Each of them differs, could be similar information, but in different data formats, data schemas. These are then sent as files to the middleware. That means in this step, we can channel everything into one kind of information provision chain, but internally we have still the data heterogeneity. And then what happens is that we apply the semantic mediator, which receives from the middleware via Kafka this kind of data. It uses internally mapping rules, what are already introduced with a self-description. It uses the domain ontology, which is very stable for example, for time series data. These are the inputs, and for the semantic mediator, what he just generates is always semantics annotated data. And at the end, this results then in an ontology. It also results in a JSON file, which is also stable and can directly be used for all following services, because JSON is the standard format for everybody in the microservice world. That means we can send this information translated on the fly to the tools, enabling with this also on the streaming side with real-time data, this kind of interoperability. And we also enable the storage inside the KBS. That means we can store the semantic uplifted data for a long time. And with this keep naturally also a huge set of historical data, which looks the same, but could come from different machines. That means if you have machines which belong to different generations, then they have different formats, but inside the KBS, you would find at the end the same format, the same way of information representation for all your machines, independent what it was at the beginning. Okay, this is the complete flow, and we will show it later on an example. And now I would go give back the ball.
Yes, thanks, Marco. I don't know if we want to provide a demonstration directly here, or we have the demonstration inside the next section. Please let me know how we can proceed. In any case,
we're gonna do a section where we're gonna discuss the pilot. So I don't know if you guys want to wait a little bit for the data analysis, and then we go over the pilot. That's okay.
Okay, thanks.
I'm gonna share the screen again. Okay, let me continue. Okay, thank you, Stefano Marco, for this very interesting presentation. Now we're gonna move to data analysis with Maria Sarodimu from Atlantis and Ioannis Metanis from Core. Maria holds a bachelor's degree with an integrated master's degree in electrical and computer engineering, and since 2020 works in an R&D department for Atlantis Engineering. Her expertise spans across two major domains: full stack development and data analysis. On behalf of Atlantis Engineering, she assumes the role of technology manager, closely working with ESMA, ISOCON, TRIMEC, and Toshulin in the field of predictive maintenance. In today's webinar, Maria will showcase the practical implementation of predictive maintenance strategies and solutions and the impact they can have. Ioannis is a senior data scientist in Core IC. Ioannis holds a PhD in control theory and design and a master's degree in systems and control from City University of London, UK. Since 2012, he has been active in research and European projects implementation, such as energy systems, NTD imaging applications, and industrial process control. His main interests are in the boundaries of artificial intelligence, with advanced control theory and machine deep learning applications, including also modeling simulations and optimization for complex systems. Maria and Ioannis, the floor is all yours.
Thank you. So let me just start by sharing my screen. Please let me know if you can see my screen
Yes, we
and
can.
presentation
Yes.
mode. Great.
Yes, fine.
Great. Today I will present you the solution that Atlantis did in the premises of the Level Up project concerning predictive maintenance. Specifically, we developed a predictive maintenance platform that contains various functionalities that we will see in this demonstration. But first, let me say a few words about us. Atlantis Engineering is an SME that provides software solutions for the maintenance, predictive maintenance, predictive quality, and optimization of asset life cycle. We also provide decision support systems, and we have an experience of more than 20 years supporting hundreds of technical departments and by participating in collaborative Horizon projects. Our aim is to develop a platform and develop a tool that can increase the lifespan and reliability of assets by adopting Industry 4.0 technologies. And that's what we aim to do in this project too. So just a few more words about what we did in project, what we worked with, what we developed, and what we had in the end. So in the project, we developed and implemented a predictive maintenance platform that contains three basic analysis pillars. The first one is a fault detection analysis section that contains both unsupervised and semi-supervised techniques. In this service, our goal is to detect in an early time any abnormalities or faults that occur to a machine. Then we have some case-specific analysis. In this section, we will mention some specific analysis that we did for cases such as vibration analysis, or for more specific sensors like the fiber optic sensors that we did in this project. Fiber optic sensors analysis that we did in this project. And finally, we have the time series prediction service, which is which contains supervised techniques, and its goal is to forecast the state of the machine in the upcoming future. The measurements that we had the opportunity to work with during the project and through the various pilots were oil particle quantity measurements, acceleration and vibration measurements, force evolution, geometrical characteristics of a machine, temperature, and pressure measurements. Now, just a few more words about the different analysis aspects. For the fault detection service, we have developed four main fault detection techniques, each one with its different type of characteristics and functionalities. The first one and the most basic one, someone would say, is the rule-based fault detection technique. In this service, we have thresholds that are derived either through a desired target value or by communicating with domain experts, or we have thresholds derived from statistical metrics that we did in order to be more close to the actual data set. Then we have spike-based fault detection service. This model utilizes a microcluster-based continuous outlier detection or else M-code algorithm. And it's a clustering algorithm that is suitable for streaming online incoming data. And it is also suitable for multidimensional measurements. And we also developed moving average space fault detection technique. This one calculates and utilizes the average value, either that is the plain average value or the weighted average value, as well as the standard deviation in order to calculate dynamic thresholds. These dynamic thresholds can be either on a warning level or on a criticality level, and it is suitable for multidimensional as well as one-dimensional data. And it was one of the techniques that we had the chance to enforce in different cases. Finally, we have the profile-based fault detection technique. This is a technique that is the semi-supervised, the most semi-supervised of them all, which has a sample of historical data, and it can calculate the distance of the newly incoming data with the sample that it has. By doing that, it can tell us if the new incoming data are healthy, considering the past, or if they are considered abnormalities or outliers. This technique can automatically update its profiles. For example, here in the picture right below it, you can see with green lines cases where the profile was updated automatically by the algorithm because as you can see below, the behavior changed. And we have also dynamic thresholds in this case that the algorithm calculates depending on what it considers the best. Moving on, we have the case-specific analysis here. We did some vibration analysis for our vibration and accelerometer data. What we did was do a frequency domain transformation and filter those data. And once that occurred and we did a frequency cutoff, the results were then forwarded to the fault detection service. So these two cases can interact and, like puzzle pieces, create a bigger functionality that gives us exactly what we would like to achieve. And for the fiber optic sensor analysis, we noticed that in the fiber optic sensors, there were patterns that we could utilize for our analysis. So what we did here was to implement a pattern recognition and isolation service that utilizes either change point detection algorithms or Muin's algorithm for similarity search, or else mass algorithm, in order to identify when there is a pattern in a dataset. In this case, especially for the CPD, the change point detection algorithms, we also did we automated the process by developing a tuning mechanism. And the results were quite satisfying. You can see a screenshot of what the results were like and the patterns that were identified below. We then filtered the data based on the pattern recognition and isolation results, and we forwarded the results to the fault detection service, specifically the profile-based detection model. Finally, the last pillar of the analysis that we did in this project and that we implemented in some of our pilots is the time series prediction service. This is a service that contains an encoder-decoder neural network model that facilitates dynamic retraining based on the forecasting accuracy, meaning that when the model considers that something is not that accurate and that the error has risen quite a lot, then it can trigger retraining functionality if that is what we desire. This makes it so that we have quite high accuracy and quite low root mean square error indexes, as you can see on the two photos above. And we also, through this service, we also provide configurable parameters for the future horizon forecasting, meaning that depending on the case, we can have different tasks that can look in different future horizon. For example, you can look in some hours ahead or some minutes ahead and take the results of both. And this is completely configurable. Last but not least, in some cases where we had multiple spike fluctuations, and it was difficult for the model to catch exactly the spike fluctuation, what we did was calculate the average value, because the average value was a good enough depiction of the state of the machine, and forecast the average value. A case like that can be shown in the two images, in the two last images, where you can see the forecasted average value compared to the actual data set, for example, in the 1 hour ahead screenshot, or compared to the actual dataset average value. Now, all these functionalities, but as well some more, like fetching the incoming data from the middleware and from the semantic mediator's output topic, transforming or pre-processing the data in any way, reporting the results and the raw incoming data to an influx database in order to have them and to have the historical data. All these are supported in our predictive maintenance platform. Specifically, the platform is based on microservices architecture, thus promoting versatility and extensibility. It can work each service like puzzle pieces. For example, the fault detection service is a puzzle piece, and the vibration analysis is another puzzle piece. So depending on the use case and on its pilots and its users' needs, we can provide you a completely custom to your case platform. Moreover, we have user authorization in order to handle the different leveling of security, especially in what panels each role can see, effortless initialization and monitoring of the analytical tasks, and seamless integration of Grafana, as well as some custom visualization panels that we developed. In the pictures on the right, you can see a Grafana monitoring panel that we prepared for one of our cases, and on the picture below, you can see our custom visualization panels, which we did especially for the multidimensional data because it was easier for us to do a custom visualization panel for multidimensional data since Grafana could not handle it that well. So that was a short presentation of what we did in the project and what the predictive maintenance platform can offer. And in the next section, which is a demonstration of our platform, I will have the chance to show you a little bit more information concerning the platform. So that was all from me. Thank you for your attention, and I'm looking forward for the questions in the question section.
So I think I will take the floor now.
Yes, you will. You can go ahead.
Okay. Perfect. So allow me to share my screen. Unfortunately, I have to quit and reopen to share my screen. I'm sorry about that. Or maybe I can do it. Okay, nice. So I think I did it.
Yes, your answers works fine.
Okay, perfect. So the overview, the contents of my presentation is we'll go quickly through the data infrastructure and the data flows to support our predictive maintenance tools. We'll see the typical machine learning workflow that we're using for developing such predictive maintenance applications. A very brief overview of some typical data analytics pre-processing and some common modeling approaches for predictive maintenance tasks, and a real anomaly detection use case. And we end up with a discussion and your questions. So very briefly, the benefits of predictive maintenance and data analytics tools stems from the fact that we can reduce the machine downtime in production, and this can save a lot of money for the pilots, for the pilot lines, and at the same time increase the productivity and make the operations more productive and machines more efficient. In general, machine learning tasks for predictive maintenance categorized into two main classes. We have the unsupervised problems where we have no ground truth or labels available, and the supervised ones where we have some labels in some format, either a digital or any other format that we have to parse. Usually from historical maintenance logs, which are kept by the operators. In practice, such logs are quite sparse, however. Some typical predictive maintenance problems are the following. We want to predict if the equipment or machine will fail in the next end period. We want to predict if the equipment will fail in the next end period due to a specific fault in a specific part or element of the machine. So in that case, we have fault prediction and fault classification on the same time. We want to predict the time to failure or the remaining useful life of the equipment. We want to detect abnormal events or the so-called anomaly detection task. And also we have the machine state forecasting, where we want to forecast either some specific measurement or state of the machine some time ahead. Here we have the data infrastructure that supports our predictive maintenance applications. So the data flow starts from the middleware that is maintained by Holonix. Here is where all the sensorial data of all the level up machines are collected. Then we have the streaming data connectors and the Kafka message brokers, where perform the data retrieval from the specific topic of the specific pilot line that we have requested. And these data are further stored, pre-processed and stored in our local database for further usage, for exploratory analysis, for data analytics tools, for training our machine learning algorithms, condition monitoring, visualization, dashboards, etc., etc. And here you can see also an example of an event, of a message that we have received. As you can see, it has a specific structure. So we have the message time, that is a Unix time format, the correlation ID, which maps this event with a specific pilot line and a specific machine. And we have also the payload, which is the actual time series data corresponding to this timestamp. Apart from the data infrastructure for the incoming data, we have also set up an infrastructure for the inference distribution services. So here we have the batching service that is responsible to prepare a batch of data in a suitable format in order to feed to the deep learning models and make inference. So then we have the inference production service that takes this batch from the batching service and communicates with the inference model server. This is where all of our models, machine learning, deep learning, etc., are integrated and communicated as a service, actually, with the rest of the services in the production environment. So it can be communicated either with HTTP or gRPC protocol. And then we have the result of this inference is persistent to our local database for further monitoring the performance of the models and create visualizations, etc. And finally, the inference outcome is distributed using the inference distribution service back to the Holonix middleware to the specific pilot line topic. Here you can see a typical machine learning workflow that we follow when we have to develop such predictive maintenance applications. So after we have collected all the necessary information, all the raw data and the maintenance logs that we need, we enter the first phase of development, that is the data pre-processing phase. So here we make several iterations. We test different pre-processing schemes, and when we are happy with our data set, we can move to the next step, which is the feature extraction. At this step, we use this step to create engineering features and that extract meaningful information from the raw data in order to be able to train our models. So having done all that, we can enter the second phase, of which is the algorithm development. Here we use the prepared data set and the engineered features, and we apply different algorithms, different models, and we iterate here for finding the optimal model and the optimal hyperparameter. And having, after all these iterations, we have a bunch of models and algorithms available. So we have to select the best one based on the KPI or a metric that we have set. Or even better, we can select our best top N models and fuse them together and build a model ensemble. So we fuse together predictions from from multiple models, and this will make the final model prediction more robust and more accurate. And on the last phase, which is the production phase, when we are happy with all this result, we package our models, we export it to the required format in order to be able to be read by the inference model server. And we deploy it to the production environment so it can be ready for real-time inference. Here I have some indications of analysis on vibration signals. I won't stay more here. I think it will be covered very comprehensively by Maria before. Some typical input features or data that we have available in predictive maintenance applications are acceleration, vibration, or acoustic type of signals. Usually also we have some temperature, pressure sensors, speed or power, even sensors for the whole machine or for the part of the machine. Then, of course, using this raw sensorial data, we can create handcrafted features. For example, using aggregate statistical measures from long time sequence in order to capture some temporal patterns. And some typical algorithms for predictive maintenance. There are some traditional unsupervised machine learning algorithms like clustering type of algorithms. And there are also the deep learning based model architectures with encoder-decoder structure that can be in many different variations, depends on their layers and their design. Here we have a typical deep learning autoencoder based architecture end-to-end. You can see here the whole data flow. So starting from the incoming data, we have a multivariable time series signals. We make some pre-processing, feature engineering, and windowing, as we call it. So we prepare batches of data in that kind of tensor format, 3D format, and we train the deep learning, the autoencoder model, where through this training and encoding decoding process, the model is able to identify the noise and discard and reconstruct a new representation by discarding the noise and keeping only the useful signal. At the output here, we have a reconstruction error output, which is a float number. And by setting a threshold here, we can turn this result to a binary outcome. So we can have a decision if it is a normal or abnormal event. And here we have an example of an abnormal event in a production environment. This particular was for Lucchini code. With a blue line, we can see the reconstruction error. This is the output of the model. The higher this value, the more probable is to have an abnormal event. As you can see here, the model, based on the initial threshold that we have set, has surpassed the threshold early on this date, around 6 o'clock. And later on the same day, of course, the reconstruction errors we can see increased a lot, past around 10 times the threshold that we have set. And by cross-correlating these timestamp events with the maintenance logs by Lucchini operators, we can see that the operator have indeed identified a specific fault, both in A and B here. So the red regions here indicate the time frame where the operator has reported that we have a true fault in the machine, and there is the downtime, the machine downtime. And yes, similarly for the next day for the event here, the model has detected the abnormality a bit afterwards, or just right on the fault, and continue to see an abnormal event up to the next day, where they have fixed, they have finalized the maintenance and come back to the normal operation. And I think that is all from my side. Sorry if I used more time.
Well, that's okay. Thank you so much. Thank you, Maria and Ioannis, for this insightful presentation. We now have a minute for taking questions on the topics that we have been presenting and discussing. So please, if you have any questions, raise your hand and I will give you your turn to speak and ask the question. If there are no questions, we're gonna now move to the presentation about the use cases, the pilots that we have discussed so far. We'll start with Atlantis and the first pilot, their demo. Maria, the floor is yours again.
Thank you. I don't know if we want to start with the demonstration of the predictive maintenance platform, or if perhaps Holonix or George from SenseUp would like to demonstrate something before we go into the platform. So
yes, we can present the data flow before the analytics and Atlantis analysis. So I can share my screen to showcase the.
Yes, you can go ahead now. Are you able to share your screen?
Yes, wait a minute. Okay. Can you see my screen?
Yes, we can.
Okay. First of all, we will start with the architecture of the pilot. As I told previously about the protocol 0, we have to prepare the pilot line in order to be ready for the level up, let's say, to functionalities and components and services. The first part is the design of the architecture based on the initial one, on the existing one in the pilot line. The architecture, as you can see, follows the typical 3 layers part, the modernization part, the middleware part, and the analytics part. Regarding the modernization part, let's have a discussion here. It is related with the sensorization, and here we can see a summarization of all activities, all that happens during the modernization of the pilot. As I mentioned previously, we have three layers of modernization: the sensorization part, the CPSization, and the gateway layer. Regarding the sensors, there are installed 35 sensors in total, 14 existing sensors and 21 new sensorial. Of course, all these sensorial are selected based on the requirements of the pilot during the project. The second level, the second layer of modernization is the CPS layer. The CPS layer, as I mentioned before, is the control unit, let's say, layer, where here we have a PLC with an OPC UA server embedded on this PLC that acts as a CPS. Of course, here we should mention that a full modernization of electrical equipment performed during the project, new electrical cabinets, new wiring, and etc. Because we need to support the whole solution. Also, as a second CPS, we installed the IMENS Vision system that is responsible for the quality inspection part. Okay, we will not deal with this now, but it is part of big part of the modernization. Finally, to the upper layer, the gateway is installed in order to collect the data coming from sensors and processed through the CPSs. And a monitoring dashboard was developed for the operators in order to monitor in a real-time basis the production line. Let's go now to the, okay, here it is the second part of the ISOCON architecture. As we mentioned previously, we have the modernization which collect data from any kind of sensorial in the pilot line, and all these data are sent to the middleware in order to homogenize all these various data sources. Here I will give the floor to Stefano and Marco in order to present the middleware part of the solution in the ISOCON pilot line.
Okay, thanks, Giorgio. If you can go to the next slide.
Yes, wait a minute, Stefano. Okay.
Yes, thanks, Georgios. This is just an overview about the application of the middleware for sensor data in ISOCON use case. As we said before, the middleware is the main layer of integration from one side for the devices and the machineries, and from the other side from the application that are delegated for analysis, diagnostics, and prognostics. Here we can see that it is a point of integration between the data source gateway provided by SenseApp, responsible for collecting data from sensor, actuators, PLC, laser profile, and so on, the ISOCON machinery, and in general the level of platform and services. It distributes real-time sensor data that are gathered from the field and expose streamed information in real time to the other modules, in particular to the predictive maintenance, the MECA and the DSS module that are going to perform diagnostic and analysis on the data. The collection of the data on the middleware is based on the definition of some element and data schema for for the information that is flowing. And so there is also a validation phase for the data that are going inside the middleware on the base of these schemas. And in particular here, you can see a snapshot about the data that we are collecting from Isocon and about data vacuum, so on. Then there is the part of management of the middleware, and after this, there is the part of data transformation and interoperability provided by the semantic mediator of Viva. So I would like to ask Marco if he wanted to present his demonstration part regarding the semantic mediator.
Yes, would be great. Okay, could we go to the next slide? Okay, go. I saw already go. Okay, this is slide I presented before. This is just how the data flows. And that means after the middleware, after we receive this heterogeneous data, we start this kind of data transformation. This is what I will show on an example. Could you go to the next slide? Okay, in principle, what happens is our mediator contains of two parts. The first part is the Kafka to mediator module, which just receives continuously the data from the middleware, and then triggers the semantic mediator to make this kind of transformation. It means if you change the kind of channel or the median, then you will just replace the first node. Could also keep this kind of semantic data uplifting. Could you click? And that means what we did for this pilot or for the all other pilots, we just started for each pilot this kind of 2 microservices on our cloud infrastructure to capture the data transformation for the pilot, and could in theory just add for a new pilot, just start new services and do the data integration out of the box. That means this just change the configuration and not changing the source code or this kind of tool settings. Okay, could you click? Could you click again? Okay, because that means what I receive, we receive this kind of data. This data is received by the middleware, and then based on this data, we just apply mapping rules. Which is part of the self description. And principally what we do is we just define a mapping, how we translate an entity of the data source into ontology concept. That means we just create a mapping for a concept, and with this concept all properties for the mapping. And this is created by an XML file. That means it's transparent. Means that data transformation is transparent because you see what will happen, because it's part of the mapping, and that means you for the future you could understand what happens for the data transformation. Okay, could you click once? Okay, the result is this kind of JSON schema, which is the same for all pilots. We have the same fields. The same for the Kafka message, but in our case, what changed between the pilots is just the labels of the observable properties and the specific values. But apart from this, it's the same schema, the same data format for all time series data, which can be received by different pilots. In this case, it's Isocon, and with this, we can feed the prediction tools to enable a simple information flow. Okay, so this was the live demonstration because we are a backend service. We have no nice UI. Everything works in the background, but what we do is really we translate the heterogeneous data into the same similar JSON schema, which can be then feed seamlessly in any tool. Okay, I give back.
Okay, covering the two first layers of the pilot architecture, now we can go to the analytics part. Just only as a wrap-up, the level up till now collects data from the field through the sensorization, let's say, process. All these data are sent to the middleware. So into the middleware, we have the homogenization of this data. And after that, all these data are available to the analytics, let's say, layer in order to consume this data and provide prediction and etc. This is the whole, let's say, level up approach for the first two layers. Of course, with the differences between pilots. I will give the floor to Maria in order to present Atlantis part.
Thank you, George. Okay, so let me share my screen. Okay, please let me know if you can see my screen. You should be able to. Great. Okay, so as we mentioned before, we have developed a predictive maintenance platform that consists of various microservices that can work together as puzzle pieces. So in this section, we will show a little bit more of the various puzzle pieces that we used specifically for the ISOCON use case, as well as the visualization panels that we did for this use case. So some of the main functionalities that we have enabled and implemented in this pilot line can be shown here, where we have the fetching of the data from the middleware of Holonix and specifically the output of the semantic mediator of PIPA. And then we have some transformations occurring where we have different type of plugins, a different type of demonstrations, and some more. And this is on the pre-processing side of the data. Then moving on, once the data are pre-processed, then we move on for specific data to the vibration analysis if it is needed, where we can choose what type of data we have, what metrics, and what we want to do, if we want just some time domain metrics, or if we want a frequency domain transformation, either with FFT or with PSD. For each case, the results of every section of the platform can be reported to either a specific database or to Holonix middleware. For example, here also the transformer, the results from the transformation and the processing can be reported to an influx database. This is also a more generic reporter where you can see all the running tasks and you can choose to add an additional reporting service. And in order to make it easier, and here we have the fault detection technique. We have different fault detection techniques. The user can pick and choose, for example, the thresholds that we mentioned before. It's this page, and the user can choose the technique they desire in order to activate that specific monitoring task. But to make it easier for the user, because this is quite time consuming and someone might not want to go to each page and activate each part of the flow, we have the batch run section where the user can provide a specific JSON with all the various microservices that they would like to see, and this will activate the responding tasks. In order to monitor now the corresponding tasks and all the analysis tasks and to just be able to see what is going on, we can go to the status page where here you can see all the running tasks categorized per type of service. For example, this is a task that makes the connection to the middleware and starts receiving data. This is the different transformation tasks. As you can see, there is a paging mechanism. You can control how many you can see. And you can also control, for example, if we would like to stop these two selected tasks, you can just stop these two, but you can also choose to stop all the related tasks. For example, if you have a detection task that expects as input the results of this transformation, you can stop the detection task 2 by just clicking here, and you do not have to do it manually later. I will not stop anything now here, and we also have the opportunity to stop all the tasks if we want. To see what is going on in each task, you can press the 3 dots and to see the details of, for example, what are the metric fields that we use, how is filtering, etc. And you can also modify some tasks. Now, these were some of the main functionalities that the platform can offer, and we can move on to the visualization aspect of it. Now, for the visualization part, we have 2 main panels that we have prepared and we have developed. The first one is a monitoring overview. In this one, you can see what is going on, both on the alerts that we get from the pilot. This is pilot alerts, but both also alerts that we have from our analysis. For example, here in the temperature 4th sensor, you can press to see more detail, and it will take you to the specific time frame of that specific sensor, and you can also see the amount of outlierness that we had. This is a red line, how much outside some limits it were. This can happen for both normal and abnormal cases. So if you would like just to see what's going on in a more detailed view, you can just press there and open it in a new window. So this is a more monitoring panel, and we consider that this is a panel that someone of a higher level, for example, an operator, that would just like color-coded notifications. That is the panel that they would use. They would get in here and they would look, okay, so I have this and this as a notification, and everything else is green, so it's good. Now, if someone would like to get more in depth in the data analysis, they could either use this mechanism with the link in order to get in that specific time frame and see what is going on, or they can go to here and go to this panel where we have all the measurements, and the user can see in detail the different measurements, the different they can play with different parameters. For example, they can select all the temperatures or just one temperature, and this is completely dynamic and based on what a data analyst or someone that is responsible for a more in-depth look of the data would like to see. So these are the 2 main panels that we have prepared, and again, we aim to cover all our levels, and a more high level, just monitoring, and a more in-depth level of what is going on with the data, what happened in the past, and the user can see all the historical data with an easy way. And that is what the platform offers. You can see we have the user must log in order to see this, and then can log out easily. And that is just an overview of the platform. So that was all from my side. Open
Thank
for
you, Maria.
questions.
I think we're only missing Ioannis for the presentation of the pilot, if I'm not mistaken.
Yes, sure. Let me share again. Okay. What we'll show you today is our monitoring dashboard, which is more intended for the data analyst for our use in order to debug the data flows, the pipeline services, and also monitor the performance of the models. Here we have an example of the Tosulin pilot line, where we have a large industrial milling machine. And we have the condition monitoring platform. On the top, we can see some alarms and specific states which are sent by the pilot line. And next we have here, of course, I should say that our task was to focus on the oil particles and the condition monitoring of the oil lubrication system, and actually precisely forecast the oil particles for different micrometers. So here on the left, on the left column, we can see the true sensor measurements, which are with blue, and the model predictions, which are the orange points. And also we have the thresholds for warning and critical that have been set using suggestions from Toslin operators. This is the model that predicts 30 minutes ahead the oil particles of 4 micrometers. And on the right side, you can see also the summary, the distribution of the errors. So in that case, we can analyze if all the errors are close to 0, or we have some very large, big errors that we need to take into account. Also, there is a CI/CD pipeline on the back that when the accuracy of the model based on some validation set that we have already predefined drops a lot, we have starts a retraining with more recent data. And similarly for the model for the 6 micrometers, again, the blue line is the true measurement value. The orange line is the model. On the right, we have again the summary of the errors. Most of them are around 0. And similarly for the 14 as we can see, models are easier to catch to forecast oil particles of bigger size, and it's harder or it's more confusing for them to find the thinner ones. That makes sense, actually. Also, of course, the user can also select the day, time that he wants to analyze the result. I won't do it now because I'm working from remote and my internet connection is not very good, so it won't handle a lot of requests. And similarly, we have models for 15 minutes ahead. Is exactly the same visualization. And then we have some condition monitoring panels from the energy part of the machine, like the consumption of the feed, etc. And also some sensor measurements, again, regarding the hydraulic system, or again, regarding the spindle lubrication system. So that is all from my side. I don't know if you have any questions that you'd like to answer.
Thank you. I don't know if there are any other questions related to other pilots that someone wants to ask. This is the time to do so. Yes, Martin.
Hello, everybody. Many thanks for the interesting presentation. As I'm involved in standardization, especially also for data exchange. So are you involved in any standardization activities? Sorry, can't you hear me?
We can barely hear you.
Should I repeat it?
Please.
Oh, yes. As I mentioned, that I was interesting and looking for standardization, especially for data in additive manufacturing. So therefore, I would like to ask if the group or if some of the activities are involved in standardization activities.
Here's Franco speaking from Biber. We are not involved in this kind of activities. We have experience in the definition and modeling of domain ontologies. Yeah, we have also some activities around modeling ontologies, but not exactly for data formats and data schemas.
Okay, and regarding the ontology, what kind of activities are these, or in
Perhaps my colleague Chen can say a couple of words, because he's involved in this kind of domain.
That's mostly related to the level up protocols that develop in the project, and also about the data thread. And another part is about the measurement. That means about how to model the sensors and their value from sensors and so on.
Okay, perhaps I can I can type my email in the chat. Perhaps you can contact me. That it would be interesting to get more in detail.
Yes, thanks. We will contact you.
Thank you very much.
Stefano from Olonix. In general, regarding the standardization of data, we are also working on IDS, so International Data Space, regarding the creation of a data space for a secure exchange of data. And it is another direction regarding data exchange, data format that is driven by IDSA, that is a partner of our consortium.
Okay, yeah, thank you very much.
Are there any other questions that you guys would like to ask? Well, I believe there are no more questions, so I would like to thank you all for participating in this very interesting workshop. And if you want to know more about the Level Up project, we have a website, levelup-project.eu. And we would also like to visit the Digital Factory Alliance website, digitalfactoryalliance.eu, for more information. Thank you again, and we'll see you in the next workshop, which is going to be held on Monday.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you very much. Bye.
Bye-bye.
Bye.
Thank you.